Hello, I am Rui Cardoso, Senior Lecturer for Aerospace Engineering. This face you are seeing there is my face, and I'm going to introduce you to statics. So I'm going to show you some sample lectures and tutorials on statics. So if you want, for some reason, to email me with any query, you have my email address here. You also have these Instagram, Snapchats, Facebook, Twitter, things for Brunel, which you can try to follow. So what I'm going to cover in these sample lectures and tutorials is basically material for your year 1 at Brunel. So I'm going to cover statics only. Of course, you are going to do many other things, but the main topics I would like you to focus is basically the first 3: vector analysis. I'm going to give a very quick review of vector analysis with the basics. And then I'm going to move to equilibrium of a particle, where a lot of vector analysis is required. Then I will introduce moment produced by a force vector. So these are quite basic but extremely important concepts that you need to know very well for the remaining of your lectures. Then I will move to the equivalent system force moment, where you will learn how to basically build an equivalent system that is in the same equilibrium conditions as the original system. That will be very important for the topic that follows, which is equilibrium of rigid bodies, which is the main topic in statics. We will study many different types of supports. The bodies, or the rigid bodies, they need to have supports. They cannot be levitating in the air. And then we are going to learn how to replace those supports with forces, which are called reactions. And we are going to learn how to derive the equilibrium equations. Basically, these equilibrium equations will make sure that your body is in equilibrium. And then from those equilibrium equations, you can calculate many different unknowns. Then we will talk a little bit about beams. We will derive the transverse shear force and bending moment diagrams for beams. So this is a kind of introductory video I will have for all these sample lectures. Of course, different lectures will have this same introductory video, but they will refer to different topics on this table of contents if you want. Another thing you can, if you are more curious, I have a YouTube channel which you can, if you are interested, of course, and curious, you can try to see what I have there. So I have a lot of lectures in that YouTube channel, so you can search for that channel by googling Rui Cardoso YouTube. I have lectures for more advanced years, so I recommend at this point you not to see those lectures. But I also have some supporting material for statics in year 1 there in the YouTube channel. So I think is a nice thing for you to see as well. I would like also to say that all the examples I will be doing in these lectures and tutorials, not all of them, but many of them were taken from these recommended books I have listed here in this slide. So Engineering Mechanics Statics from Ibler, or from Vector Mechanics for Engineers, Statics from Beer and Johnson, from Engineering Mechanics Statics from Marian, Bolton and Craig, and also from my own book, Stress Analysis for Lightweight Structures, a MATLAB-oriented approach. So all the examples you will see in the videos, sometimes I refer which book I've taken the example, sometimes I don't, but these are the books that I follow. So in case I forget to mention which book I took the example, you have here the list of books, so you know where they came from. Right, thank you. So we will move now to the specific lecture.
So I want to introduce you now with one of the most, well, you will see I always say this for everything. Everything is important, but really this one is a very important issue which you sometimes struggle to get it right, which is the moment produced by a force. And before I start writing something there, I would like to tell you what is really a moment produced by a force. So imagine this is a force, okay? I'm applying in the upwards, in vertical direction. And I want to calculate the moment produced by this force about this point, okay? So that moment is going to be equal to this force, or the magnitude of this force, times the distance, okay, the distance perpendicular to the force, right? So if I apply a force like this, this system that you see here in my hands, it tends to rotate in this direction, right? So if it tends to rotate in this direction anti-clockwise, we'll say the moment is positive. If the force is downwards, it tends to rotate the system clockwise, right? So we'll say the moment is negative, all right? So a moment produced by a force is basically a force times a distance in very, very gross terms, right? A force times a distance. The higher the distance, for example, imagine I'm calculating now the moment about this point here. So my distance is much higher than the previous one, right? It means my moment about this point will be higher than the moment about this point for the same force. Yeah? Right? So the moment depends on two things, basically. Depends on the force and depends on the distance of that force to the point where I want to evaluate the moment. The higher the distance means higher the moment. Higher the force means higher the moment. Okay? Let me give you an example. A torque is also a moment, right? Imagine, for example, you have something like this. Okay, imagine your car. So you have the floor here, you have the wheels. Imagine this, all right? So what happens to your car? So you have the engine here somewhere inside, right? It's giving a torque to the wheels, right? Through the gearbox and all of that stuff. So what is happening is you are putting on the wheel, you are putting a torque like this. We call T, but this is in fact a moment. And why does your car move in this direction? Why does it go in this direction? Because the wheel is making a force on the ground, on the floor, in this direction, and the ground will react, this is Newton's third law, will react on the wheel with a force in the opposite direction. Right? So this force is because of friction between the tires and the floor. So this is Newton's third law. So how do we calculate this torque? So this torque, T, basically is going to be what? Is going to be, so imagine if the wheel has this radius R, is the radius of the wheel, this torque is going to be equal to the radius times the force, this force F, right? This is the definition of a moment. It's a force times a length, in this case is the radius of the wheel. And that will give you the torque that you need. So if you need this force to move the car in the front with some velocity, with some speed, you know the radius of your wheel, so you know the torque that your engine needs to deliver to get the movement of your car, right? So this is the definition of a moment. In this case, it's a torque, which is the same thing as moment, right? It's not only a force, it's a force times a distance, a length. This is a moment. And when you do the cross product to obtain the moment, you always have a position vector with a force vector. That will give you a moment, right? So I hope that you are not so confused now. I don't know. But anyway, we will do more examples. So I'm going now to define the moment produced by force in a very general way. So imagine you have a force here somewhere, let's say force F, applied, for example, at this point A. And I want to calculate the moment produced by this force about this point O. So my aim is to get the moment produced by this force F about point O. We usually tend to write like this. M is still a vector. It's going to be a vector. And subscript O. It means I'm evaluating the moment about point O. All right? And that moment is going to be equal to a cross product, which you learned last week, between two vectors. The first vector is a position vector connecting point O with point A. I will call it ROA. All right? So we can say the moment is going to be the cross product of this vector ROA, cross product with the force vector, cross product with F. All right? And then the result, so imagine if this is a problem in 3D, in 3 dimensions. For example, you have these 3 axes. The result of this moment is going to be a vector with a component in the x direction, a component in the y direction, and a component in the z direction. Okay? So the only thing you need to do to get the moment is you need to get this position vector that you have there in green defined, connecting 2 points. Always starting on the point where you are evaluating the moment, in this case point O, and ending at the application point of the force, in this case point A. All right? You define a position vector. The other vector you need is the force vector, which should be given to you. And then the only thing you have to do is just to do the cross product, and everything will come automatically from the cross product. And the best way to show you that is by doing an example. This is an example which I will upload in Blackboard. So I have the solution, which is a solution very different from the one I'm going to do now with you, okay? I'm going to use, for the solution of this problem, I'm going to use the cross product to get the moment. But I will upload in Blackboard 2 different ways of getting the moment without using the cross product, which is convenient in 2D. For 3D, I don't recommend doing this. I recommend doing the cross product. But anyway, I will upload this in Blackboard. It's also in the video lecture from last Monday. I solved this in this way Monday. Here we don't have time. I will be solving only the cross product to get the moment about O. So the question here is, what is the moment produced by this force F of 5 kilonewtons about this point O here that you see on this strut? Okay? So that is the question. And we are going to solve this by using the definition of the moment by doing the cross product of a position vector and a force vector. So the first thing I'm going to do is I'm going to define the position vector. So where do you think it should start? This position vector in green that you have here, for this example, needs to start where? Where? Point O, right? So it needs to start in this point and needs to end where? At the tip of the strut, right? So it needs to be a position vector like this. You agree with me? This one in green? Starting at O, because I want to evaluate the moment about point O. So the position vector needs to start at O. And it needs to end at the tip or at the application point of the force, which in this example is at the tip of my strut. Okay? So I can start immediately to define this position vector. Let's call it, so let's give a name to this, RO. So let's say this is my point A, ROA, okay? And let's define it here. So this is going to be my x-axis, y-axis. We need to have a coordinate system. We are working with vectors. And the z-axis is perpendicular to the whiteboard, right? So this vector, ROA, will have a component in the x direction. How much is it? The length of, or the norm of this position vector is 3 meters, right? You agree all with me? So the x component is how much? 3 cosine, very good. Is 3 cosine of 30 degrees, right? This is my x component. What about my y component? The component in the vertical axis. So if I decompose this vector in the vertical direction, I'm looking for this vertical component of my position vector. Sine times 3, right? So my vertical component is going to be 3 sine of 30. And the z component. Do I have any component in the z direction? No. So I will say 0. So my position vector, it is defined like this. Okay? Any questions on position vector? The next thing I need to do is I need to define my force vector. My force vector F will also have a component in x, y, and z. Z is 0 as well, right? You agree with me? So I can put in z direction, I can put 0. But in the x direction, so what I need to do, I need to decompose my force vector in the x direction to get that component there. You all agree? How much is the magnitude of F? Or the norm is 5. So if I want to get the horizontal component, 5 cosine of 45. Yes, very good. So I will have 5 cosine of 45 degrees is my x component. My y component is this one. Agree? Positive or negative? Negative, right? So minus 5 sine of 45 degrees. That's it. My two vectors that I need for the moment, they are completely defined. What I'm going to do now is I'm going to do the cross product. I'm going to do this cross product in order to have the moment about point O produced by that force. So these two vectors, they are completely defined, so I'm going to write them here again. Cross product with the force vector. And the only thing I have to do now is the cross product, and everything will come automatically. You don't need to worry if the moment is clockwise or anti-clockwise, if it is positive or negative, because the cross product will give you everything automatically. All right? So let's do this cross product very quickly. So the x component, I will ignore the x there, and I need to do this cross product, right? Which is going to be 0. Look, I'm multiplying 3 sine of 30 with 0, minus 0 times minus 5 sine 45, which is also 0, right? So the x component is going to be 0. For the y component, I need to do this cross product. So I will ignore the y components there, and I do this cross product. It's going to be again 0. Yeah? Agree? For the z component, I need to do this cross product. So this is not going now to be 0. This cross product is going to be equal to minus 3 cos 30 times 5 sine 45. Minus 3 sine 30 times 5 cosine 45. So this is my moment about point O. Okay, so this is my moment about point O. And as you can see, in a 2D problem like this, the only component of the moment that is not 0 is the z component. Does this make any sense or not? Let's see if this makes any sense. What did I tell you last week about cross product? I told you that the cross product of two vectors, the result, which in this case is the moment, needs to be perpendicular to both vectors, right? So the result needs to be perpendicular to both the position vector and both the force vector. If you look at this figure, the position vector and the force vector, they are both in the xy plane, right? So the only option for the moment to be perpendicular to these two is to be a vector with component in the z direction only. And this is confirmed from this result of the cross product. You only have a component in the z direction, which is the moment, okay? All right, to recall again, what is the definition of a moment produced by a force? So imagine you have this force applied at point A. You want to calculate the moment produced by this force about point O. All right? So we have seen last week that if we define this position vector, we can say that that moment is equal to the position vector cross product with the force F. Right? So we did even one example last week, a 2D example, where we could see that we only got, so this moment is a vector, so we only got a component in the z direction for 2D, right? The x and y components were 0. Right, so I'm going to now do very quickly one more important thing. Imagine we have this force F applied at 3 different points. So I'm going to copy. Imagine this situation here, for example, where we have force F applied at point A here, at point B, and at point C. So this is the same force F, but just applied at 3 different points. And of course, this force has the same direction, right? So it has the direction of this red line, right? So imagine this force F applied along this red line, but applied at these 3 different points, A, B, and C. And our goal now, imagine, is calculate the moment about this point O produced by this force F. All right? Going back to this definition of moment, if I want to calculate the norm of my moment, or the magnitude of the moment, it is given by the magnitude of the position vector times the magnitude of the force vector times the sine of the angle between the two vectors. In that case of this example, will be this angle here, alpha, right? The angle between the position vector and the force vector. So we did this 2 weeks ago, I think, when we discussed cross products. So you are well aware of this. So I'm going to use this equation here for the norm of a vector. In fact, And then what I'm going to do is I'm going to define these position vectors. I'm going to define the vector ROA, connecting point O about end point A, which is the application point of the force. I'm going to define another position vector ROB and another position vector ROC. Okay? So I have this force F applied at 3 different points, and in order to calculate the moment about O produced by these 3 forces, I will have these 3 position vectors. Eh? You agree with me? And what I'm going to do now is to basically calculate I'm going to paste here. I'm going to calculate now the norm of the vector. I'm just going to do one thing. Just going to write like this, okay? Because it will be easier. Now let's look first at this position vector that we have here, ROA. All right. So if I want to calculate the moment produced by force that is applied at point A about point O, I need to use this position vector ROA, and my angle, this angle alpha that you have there, is going to be this one. You agree with me? Yeah, you agree with me or not? It's the angle between the position vector and the force vector, right? Now look at this. This ROA sine of alpha is going to be, so if I draw this, so this ROA is the hypotenuse. If I multiply the hypotenuse by the sine of alpha, what I will get is this distance in the perpendicular direction to this force, which I will call distance D. Right? Isn't it? Now, if I look to the moment produced by the force applied at point B, I will have norm of the force, times my position vector now ROB, times the sine of, let's say now, angle beta. And that angle beta that I'm looking for now is the angle between ROB and my force F, isn't it? Is this angle. So again, ROB sine of beta is going to be my distance D in the perpendicular direction to the force, right? If I do the same for the moment, the norm of the moment, when I look at my position vector ROC, I will get norm of F times norm of ROC, which is the position vector, times sine of gamma, where gamma is going to be equal to this angle here, gamma, right? So ROC sine of gamma, again, is going to be equal to this distance D. Okay? So the conclusion is, it doesn't matter where I put my force F, if I put at point A, B, or C, or any point D, E, F, whatever, as long as it is along this line in red, the moment about point O, or the norm of the moment, is going to be always equal to the norm of the force times the distance in the perpendicular direction to that line. Okay? This is especially convenient for 2D analysis. For 3D analysis, I always recommend you guys to use the cross product. For 2D analysis, you can, because you know the moment vector will have only a component in the z direction. For 2D, you can go directly and calculate the magnitude of the moment, or the norm, by just multiplying the norm of the force by this distance d perpendicular to the force direction. Okay? So this was a kind of demonstration I wanted to do with you.